how do you run a microwave oven that requires thousands of volts and a phone which requires very tiny amount of voltage by plugging them both into the same supply, 230 volts main supply? I mean, the voltage is too low to run a microwave, so how does it work? And the voltage is too high for our cell phones, so why don't they blow up? The secret is a transformer. So what's a transformer? A transformer is a device that can either step up, which means increase, or step down, which means decrease, step down an AC voltage. Okay, what does that mean and how does it work? Well, at the core, the transformer is basically just two coils kept close to each other. One which is connected to the supply, an AC supply, is called the primary coil, and the other which is connected to some device which we want to run, we'll call that the secondary coil. And the basic principle is the supply voltage is going to generate an alternating current. So the current will keep fluctuating back and forth, and current passing through a coil will generate a magnetic field. And that magnetic field will also fluctuate because the magnetic field depends solely on the current. And because of that, Mr. Faraday comes and says, changing magnetic flux through a coil, there will be an EMF induced. So an EMF gets induced in the primary. But what's also important to understand is that that same magnetic field will also get linked because the second coil is kept very close to the first one. It'll also pass through the secondary. And as a result, as the flux changes over here, as the magnetic field changes over there, the flux also changes in the secondary. And again, an induction takes place in the secondary. And because of that, there will be an EMF generated in the secondary. And as a result, there will be a current generated in the secondary. And that's how the bulb starts glowing. Now at this point you might say, hold on a second, what a waste of time. Why can't I just directly connect the supply to the bulb? Wouldn't that be just easier? Well, if you do that, then the voltage at the bulb will be exactly the same as the voltage that you are providing over here. And that's not what we want. We want to be able to either increase this voltage or decrease the voltage. And that's the idea behind a transformer, either step it up or step it down. So how do these coils help do that? Well, let's analyze the voltages at the primary and the secondary. To do that, let's start by looking at a single coil over here. We know from Faraday's law that the EMF induced in any coil due to the changes in the flux is given by E. If EMF E is the negative rate of change of the magnetic flux. It basically means if the flux changes very fast, then there'll be a higher EMF induced. That's the whole idea behind this. So this is the EMF generated in one coil. Now, if there are total, let's say NP number of coils, where P stands for primary, then what is the total EMF generated? Well, the total EMF generated, that will be the voltage in the primary. That will be just NP times E. NP times E. What about the secondary coil? Well, we can do similar calculation. We can say that through each coil, the EMF generated must be the same. Because the flux here and the flux here must be the same. Now you might say at this point, hold on, wouldn't the flux decrease because we're going farther away? Wouldn't the magnetic field lines go farther away and become weaker? You're right, but there is a way in which we can make sure that the magnetic field lines over here and the magnetic field lines over here have the same strength. And we'll talk a little bit about how that happens a little bit later, how we can make sure of that. But if we assume that the flux here is exactly the same as the flux here at any moment, then the flux through each coil, the EMF through each coil, is going to be E. And from that, we can now figure out what the secondary voltage is going to be. I want you to pause the video at this point and see if you can, using that, figure out a relationship between the primary voltage and secondary voltage. Go ahead, give it a try. All right. If the number of turns in the secondary is, let's call that as N S, where S stands for secondary, then the voltage in the secondary is going to be, well, one coil has EMF E, Ns number of coils will have Ns times E. Notice the voltages in the secondary and primary are not the same. If I divide them, we'll get the relationship between them. We get Vs divided by Vp equals Ns divided by Np. This means that if the number of turns in the secondary is more than the number of turns in the primary, like shown over here, then notice the voltage in the secondary would be higher than the voltage of the primary or the voltage of the supply. And we call this the step up transformer, increasing the voltage. That's what happens in your microwaves. Your microwave oven requires thousands of volts to run. But you might know that our AC mains supplies only to about 230 volts, so roughly around 200 volts, let's say. So if you want to increase the voltage, say by 10 times as an example, then all we have to do is make sure that the number of turns in the secondary is 10 times more than the number of turns in the primary. Step up transformer. On the other hand, if the number of turns in the secondary is smaller than the number of turns in the primary, notice the voltage in the secondary would be smaller than the supply voltage or the voltage in the primary. We get step down a transformer. And that's what you would use if you wanted to charge your mobile phone, because it requires a very tiny voltage. The AC supply gives you a lot, so you step it down appropriately by reducing the number of turns. And as a bonus, notice we're able to charge your electric phones without having a direct connection between these two circuits. Wireless charging. That's right, that's how wireless charging works. The secondary coil would be inside the phone, the primary will be connected to it would be inside the charging pad. You keep the phone on the charging pad, wireless charging. Beautiful, right? Before we wrap up, we still have to answer, how do I make sure that the flux here and here remains exactly the same, right? Now, before I do that, I have one question for you. Do you think this transformer would work on a DC supply? What if I used a battery here instead of AC? What do you think? Would the transformer work? Pause and think about this. All right, hopefully you've tried. So, does it work on DC? Well, let's see. The main principle is electromagnetic induction. And for induction to happen, the flux needs to keep changing. And that can only happen if the current keeps changing. And that does not happen in DC. And that's why you cannot use transformers for DC. You can only use it for AC. Okay, lastly, how do we make sure the flux here and here remains exactly the same? Otherwise, the equation won't work. Well, a way to do that is by introducing a ferromagnetic core. A ferromagnet has the ability to sort of suck in magnetic field lines. And as a result, almost all the field lines from the primary passes through the secondary, making sure the flux through each coil is exactly the same. Of course, in a real transformer, there will be some flux leakage and the equation will not be valid. But for our purposes, we can assume ideal transformers and work with it. And we've just touched the basics. We still have to dig deeper and think about what happens to the currents or the energy when voltage gets stepped up or stepped down, and explore how electric power transmission would be impossible today without transformers. Hopefully you're getting a sense that you can't live without a transformer. They are more than meets the eye.